Good morning. Today, I'd like to look at another application of integration. This time around, by the time we figure out how to do things, we will no longer go through the complete, detailed setup when we work problems. The issue is this. I'm going to have the graph of some function, the graph of y equal f of x, starting at some particular x value a, ending at some particular x value b, and what I'd like to know is not the area under the curve, not the volume of revolution, but I'd like to know the distance that I have to travel as I travel along the curve. Now, to be clear, I'm not talking about the straight line distance from here to here. That would be fairly easy to calculate. I'm talking about the length traveled along the curve, what we'll call the arc length. The key fact that's going to let us figure out this arc length is the Pythagorean theorem. If I have a right triangle with shorter lengths a and b, and the length of the hypotenuse equal to c, it's well known that c squared equals a squared plus b squared. So the c itself must be the principal square root of that quantity. On the other hand, this number, c, is the distance from this point to that point. So, as you'd expect, the Pythagorean theorem is going to figure into distance calculations. Since we only have one trick so far, we'll apply it again. I'll take the range of x values from a to b and divide it up into many smaller individual sub-intervals. Then I'm going to look at the piece of the graph that goes with one of these sub-intervals. As usual, I'll call the horizontal extent of that delta x number I, and since x is the independent variable in this situation, I'll pick the x equals ci to be a representative x number. The difference between this and what we've done before is I'm wanting to think about the distance along this stretch of the graph. Not only is there a delta x number I, there is a delta y number I also. This is how much the y coordinate on the graph changes when I'm looking at just chunk number I. At the beginning, I'm going to draw a horizontal line. At the end, I'm going to draw a vertical line. Take this picture and magnify it. I have delta x number I across the bottom, delta y number I vertically. I'll call this distance number I, and I have myself a nice right triangle here, meaning that I can apply the Pythagorean theorem to it. Doing so, distance number I is approximately radical delta xi squared plus delta yi squared. Ideally, we would just then add up all such things, take the limit as the chunks tend to zero in size, and turn it into an integral of some type. What I've written here is correct, but it's not in the kind of format that we usually have. Usually, we have the limit of the sum of something that explicitly involves representative value ci, and then delta xi down at the end, or sometimes delta yi, depending on what the independent variable is. I can do something about that, though, by doing some algebra. Underneath the square root sign, factor out delta x number I squared, then use properties of square roots to split this into the product of two square roots. Delta x number I is always positive, so I don't have to write absolute value of delta x number I there. I can just drop the absolute value symbols. I can further simplify this situation. If I remember the mean value theorem from Calculus 1, if we assume that f has a derivative in this subinterval, then the change in function value on chunk number I divided by the change in x on that chunk is actually equal to a value of the derivative of f. It is f prime at ci for some ci in interval number I. I'm starting to like the looks of this a lot better now. The distance that we're interested in is the limit as the norm of the partition tends to 0 of the sum of some quantity that involves c number I times delta x number I. So finally, this is the definition of an integral. The arc length, the distance along the curve that we're interested in, is the integral from a to b with respect to x of the square root of 1 plus the square of the derivative of f. I could have just written the square of f prime of x there, or it may be nicer looking if you write it that way. In either case, I mean f prime of x. For some historical reason, people like to use the lowercase letter s to represent arc length. My printed s looks so much like a 5 that I've decided that I'm going to use lowercase cursive s. So this is going to be my generic formula for arc length when the function is defined as y being a function of x. There is both good news and bad news. The good news is, for the y equal f of x situation, if the f has a derivative, which is not a very difficult requirement for a function, the arc length is given by this formula, the end. That's the good news. The bad news is, very often, even for very simple functions, you end up with an integral that you don't know an antiderivative for. In our next major section, we're going to address that problem, but for now, I'm going to be content with setting up integrals. If I know how to do the integral somehow, I'll go ahead and do it. If I don't, I may resort to some sort of numerical approximation scheme like the FNINT that's built into your calculators. As an example of the good news, bad news situation, think about the graph of y equal 1/2 x squared starting at x equal 2 and ending at x equal 3. I'd like to calculate the arc length along that curve between x equal 2 and x equal 3. The good news is it's going to be very easy to set the integral up. The bad news will follow almost immediately. The derivative of y with respect to x is 1/2 times 2x, which is x. The arc length integral will be from x equal 2 to x equal 3. If I square dy dx, I get x squared. All you have to do is integrate from 2 to 3 with respect to x, the square root of 1 plus x squared. It's at this time I have to warn you guys about something. A lot of people will do a problem, they'll get it down to this step, and then they'll start doing algebra things to it that are not true. A lot of people looking at this integral would say to themselves, okay, that's square root of 1 plus square root of x squared, which is 1 plus x. That's not how the algebra works, though. If you try that idea by sticking some various numbers in for x, you'll find out that radical 1 plus x squared is not the same thing as 1 plus x, so that idea is no good. The bad news, if you look at the list of things that we know how to integrate from Calculus 1, this isn't on the list. At the moment, there's no convenient way of manipulating it around so that it is on the list. At the moment, even though writing the integral down was easy, we don't have a way of evaluating it in the way that we've been evaluating these other integrals. That means I'm going to have to resort to some sort of calculational approximation to this answer. Luckily, if you've got a TI series calculator, they've built something in for you. Depending on the exact model of your calculator, you may have a more modern-looking math print built in, or if you're using one of the older ones, you won't. To be complete, I'm going to do this both ways. We should, of course, get the same answer out of it. Firstly, I'll say math. Among all of the things that you can do in math is FNINT, which is choice number 9 on this calculator. So I'll type a 9. FNINT wants to know some things. It's going to want to know the thing that I want to integrate. Then it wants a comma. Then it wants the name of the variable. Then it wants another comma. Then it wants to know the lower limit of integration, comma, upper limit of integration, close parentheses. Square root 1 plus x raised to the 2 power. I have to close parentheses on the square root. Then, comma, the name of the variable is x, comma, I'm starting at x equal 2, comma, ending at x equal 3, close parentheses. According to the calculator routine, the arc length that we're interested in is about 2.6947. If you have an older style calculator, this is the syntax that you'll have to use. If you have a newer one, I want to demonstrate that one too. So I'm going to push mode here. On this calculator, up at the very top, it says math print as opposed to classic. I've got classic highlighted. That's what we were just doing. So I'm going to go sideways with my cursor key between classic and math print and select math print this time. So I'll say second, quit to get out of this. Let's do the integral again. Math, choice number 9, except this time it looks like the way you would write it by hand. The blinking cursor is on the lower limit of integration, which is 2. So I'll type a 2. I'll go upwards by pressing the up key. The upper limit of integration is 3. I'll go sideways by pushing the sideways button. It wants to know the function that I am integrating, which is the square root of something, 1 plus x raised to the 2 power. Now I have to caution you, if I continued typing this stuff, it would go upstairs along with the 2 in the x squared. To get down from there, I'll just go sideways again. Then I'll go sideways again, And again, it needs to know the name of the variable of integration, which is x. Press enter. It comes back and says 2.6947, and this is the same answer that we got doing it the classic format way, which of course it should be. This is a numerical approximation scheme. It's based on something called Simpson's rule. If you take numerical analysis, I'll eventually tell you everything that you want to know about Simpson's rule. Really, probably more than you want to know. Sometimes, if you very carefully rig up the problem, you can make it into something that you can actually do in the Calc 1 sense of the term. I'm going to do an example in a moment that relies on an algebra fact. Imagine that I subtract two numbers a and b and then square the result. We all know from algebra that that is a squared minus 2ab plus b squared. On the other hand, if I add two things together and square that, it's a squared plus 2ab plus b squared. The significance of this is this. If I square a difference of two things and reverse the sign of the piece in the middle, I now have a perfect square again, the square of the sum of the two things instead. If I have the square of the sum of two things, and then I reverse sign on the middle term, I still have a perfect square, namely the square of the difference of the two things. This is going to let me do some trickery in a moment. I want to think about the graph y equal 1/2 times e to the x plus e to the negative x. Those of you who know your special functions will recognize that as the hyperbolic cosine, but we won't talk about that at the current time. I'd like to find the arc length along this curve starting at x equals 0 and ending at x equal 1. We all know what we have to do. We have to figure out what dy dx is, figure out what 1 plus the square of that is, do the square root of that quantity, and then integrate it with respect to x over the relevant range of x values. The derivative of y with respect to x is 1/2 e to the x minus e to the minus x. If I square that, I'll have two factors of 1/2, giving me the 1/4, and I'll have the square of e to the x minus e to the minus x. This is where that fact is beginning to sneak into the picture. If I square e to the x minus e to the minus x, of course, I get e to the x times e to the x minus 2 times e to the x times e to the minus x plus e to the minus x multiplied by itself. In a moment, an algebra miracle is going to happen. If I go ahead and multiply through by the 1/4, I find out that dy dx quantity squared is 1/4 e to the 2x minus 1/2 e to the x multiplied by e to the minus x is 1, and then plus 1/4 e to the minus 2x. The thing that I have to do now is I have to add 1 to both sides of this. That's the quantity that's going to be underneath the square root. That gives me the thing that I need to integrate. When I add 1 to dy dx quantity squared, I already had a minus 1/2 as a constant term. When I add the 1 in, I'll have minus 1/2 plus 1, which is plus 1/2. Then I'm going to factor the 1/4 back out, and then a miracle happens. At first glance, this looks kind of horrible. The more observant amongst you are looking at this formula saying, wait a minute, wait one darn minute here. I've seen something recently that looks very much like that. Allow me to back up for a moment. If you square e to the x minus e to the minus x, what you get is e to the 2x minus 2 plus e to the minus 2x. And what I've got as a result of this most recent calculation is e to the 2x plus 2 plus e to the minus 2x. This quantity and this quantity are the same, except the minus needs to become a plus in this formula because of that business. I'm going to take the principal square root of both sides, which is never negative. E to the x and e to the minus x are also never negative. There is no worry about absolute value signs here. Unlikely though it may seem, the square root of 1 plus dy dx squared actually works out to be something reasonably nice. We do know how to integrate e to the x and e to the negative x, so we should be able to do our arc length problem now. An antiderivative is 1/2 multiplied by e to the x minus e to the negative x. I have to evaluate that between x equals 0 and x equals 1. E to the 0 is 1. Negative of 0 is 0. E to the negative 0 is also e to the 0, which is 1. These two bits cancel each other out, so I'll ignore them. This is e minus 1 over e. A perfectly acceptable answer is 1/2 multiplied by e minus 1 over e. If you thought it looked nicer, you could write that as a single fraction, but these two quantities are the same. Not to make this longer than it needs to be, you can also have situations where the independent variable is y and the dependent one is x. Instead of saying x goes from A to B, to keep the distinction straight, I'll use the next two letters in the alphabet. It's y that goes from y equals c to y equals d that gives you the limits of integration. In this situation, you get a formula for arc length that is exactly similar to what we had in the first examples, except the roles of x and y have been interchanged. I'll do an example of this up to setting the integral up. I'd like to look at the graph of x equals y cubed. I'd like to start at this point, travel along the curve till I get to that point. It's worth mentioning that I could do this using the same style that we were doing a moment ago. I could say that y is the cube root of x. The x would go from 0 to 8. I'd have to do the derivative of the cube root, square that, add 1 to that, do the square root, and then write down the integral from x equals 0 to x equals 8. In this particular case, you could do that, but you're making life much harder on yourself than you need to. In this situation, x is determined by a simple formula involving y, I'm going to treat y as the independent variable and x is the dependent one, as it's written here. The y goes from 0 to 2. The integral will just be the integral from 0 to 2 with respect to y of the square root of 1 plus the square of not dy dx, but of dx dy. The derivative of x with respect to y is 3 times y squared. If you square that, you get 9y to the fourth. This is the integral that you would have to do. We don't know how to do that integral in closed form, so we could do it using a calculator technique. It's worth mentioning that the calculator doesn't need to know certain things. It's easiest for me when I type this in on the calculator to pretend that x is the variable. The calculator doesn't need to know that what it thinks x is secretly what I'm calling y in these formulas. If it made me feel any better about lying to the calculator, I could write down capital X for the y, with the understanding that capital X is not the same thing as little x. Of course, in reality, this is all just a bunch of nonsense because the name of the variable can't tell me how much arc length I've got. The calculator tells me, to a good degree of approximation, the arc length is 8.63032. Coming up, I'm going to have a relatively quick little video on a related topic, namely lateral surface area. After that, we will look at the last of our major applications of integrals that we'll consider, work, and then after that, we're off into the horrible and great adventure of methods of integration. Until then, I hope everybody has a good day, and I'll talk to you again soon.